Podemos iniciar. Hoje temos a honra e o prazer de ter Daniel Brandenburg. Ele se formou na Universidade de Rice no experimento STAR, estudando energy scan de colisões de íons pesados. Depois foi como postdoc no Brookhaven National Laboratory, e agora, onde está agora, também ganhou Gold Haber Prize para projeto de pesquisa melhor na física de íons pesados no último Quark Matter, na cidade agora famosa de todo mundo, de Wuhan. Ele vai falar para nós sobre, em inglês claramente, sobre uma das um dos tópicos um pouco complementares da física de íons pesados, mas muito interessantes, que é a física de campos eletromagnéticos ultrafortes. Para estudantes, como sempre, por favor, ponham no chat seu nome e seu array, porque vai ter lista de presença. Por favor, se mude, por favor, desliga o vídeo. Eu vou, durante o meeting, depois durante as perguntas, claramente, eu vou deixar vocês falar. Daniel, you can start. As soon as I unmute you, and I think... Did I just unmute you or not?
Can you hear me?
Yeah,
good. Okay, let me start by saying thank you again for the invitation. It's a real pleasure to be here over Zoom, and I hope that everyone finds this topic interesting, and I hope that I'll be able to convince you that it's a topic that's multidisciplinary and can hopefully be useful to many of the different topics of those of you in the audience. So the title of my seminar today is Probing Ultra-strong Electromagnetic Fields with the Breit-Wheeler Process. And to give you an idea of what this talk is going to be about, it'll be mostly about quantum electrodynamics and the electromagnetic fields generated by heavy ion collisions. And what I'll do is I'll just first walk through a little bit of introduction and some history behind the processes that I will talk about. And then we're going to talk about a specific class of heavy ion collisions called ultra-peripheral heavy ion collisions, and how those specific events allow us to test QED under extreme conditions that have never been tested before. And then what we'll do is we'll look at the results of some star measurements and specifically focus on two fundamental processes in quantum electrodynamics called the Breit-Wheeler process and vacuum birefringence. So most of the talk will be about these two processes. And then because I hail from the field of high energy nuclear physics, I want to connect this back to my primary field and try to demonstrate that these discoveries in QED are also valuable new tools to study quantum chromodynamics. And I'll just give a few examples of how that connection can be made. Okay, so let's go ahead and get started. When I talk about this process, I like to take a first step of looking at the fundamental interactions between light and matter. Right? This is a very fundamental set of interactions that we can look at, and there's actually only a few of these fundamental interactions between light and matter. And so, for instance, in the Feynman diagram notation, you can look at this process. And normally when I'm doing this talk in person, I like to make it maybe a little bit interactive, but I know it's hard to do over Zoom. So I'll tell you, instead of making you guess, that this, for instance, is the photoelectric effect, right? A very fundamental interaction which has had profound impact over the course of history with, solar power and solar powered cars becoming common now, and all types of different technological impact here. And I give you this as an example of a fundamental interaction between light and matter This was the first discovered in 1887. We can also look at kind of the mirror image of that diagram, which is brimstolon. So you have an electron, for instance, interact with a photon, which is bound to a Coulomb field. That's what this cross means. And it scatters and emits a real photon, right? So that's brimstolon. That was discovered in 1895. And then we can actually look, there's quite a few other processes, but like I said, there's actually not that many if we think about these fundamental interactions. So there's the well-known Compton scattering process, where an electron, for instance, scatters off of a photon. There's the Breit-Wheeler process, which I'll talk about a little bit in the context of this talk, where a real photon and a virtual photon from a Coulomb field can produce an electron-positron pair. This was proposed in 1932. There's single photon annihilation, in which you have a process similar to this, where you have an electron-positron come in, they interact in a Coulomb field and produce a single photon. You have Dirac annihilation, which is a common process that we talk about, in which you have a matter-antimatter pair annihilate into a pair of photons. And now all of these processes that I've named so far were proposed, many of them about 100 years ago or more, and they were all discovered in the past many decades. However, if you take this Dirac annihilation process and you mirror it to the process in which you have two real photons colliding to produce an electron-positron pair, this is the process that we'll refer to as the Breit-Wheeler process, which was first predicted in 1934, shortly after the prediction of the positron. And the surprising thing is that this is one of, like I said, one of the fundamental interactions between light and matter. In fact, it's the simplest process by which you can take just light, two photons, and convert that into a matter-antimatter pair. This was predicted in 1934, but there has never been, until now, a definitive observation of this process. And so what we'll do as we go through this talk is to look at this process and to see if, in fact, we can observe this in heavy ion collisions. Okay, so that's a bit of an introduction. Now I want to just give you a moment. You know, sometimes we can miss, why are these problems so hard to solve? I've just told you that this was predicted nearly 100 years ago, and yet throughout these many decades, it still has not been observed. And I want to give you a little bit of a feeling for why that is. Part of it is because the interaction cross-section for two photons to collide is actually quite small. So if you think of this in terms of meters squared, the peak of the cross-section is about 10 to the negative 29 meters squared, which is an incredibly small cross-section. However, if you think about it, it's not that different from some of these other processes which I've already pointed out have been observed. The thing that sets the Breit-Wheeler process apart is that you really need enough energy in the center of mass to produce this matter-antimatter pair, in this case, an electron-positron pair. And that's what really sets this process apart and makes it extremely difficult to achieve in a laboratory setting. And Breit and Wheeler, the authors of the original prediction of this process, they really were already well aware of this. So in their paper in 1934, called The Collision of Two Light Quanta, they already tried to grapple with this problem of how could you actually achieve this process. And in their paper, they noted that it's essentially hopeless to try to observe the pair formation in laboratory experiments using beams of X-rays or gamma rays because of how small the cross-section is and the fact that there's insufficiently large available densities of quanta. So what they're saying is that with the technology that existed at the time, it's essentially impossible to actually build an experiment which forces two real photons to interact via this process. However, they noted that it may not actually be impossible in heavy ion collisions. So I really think it's incredible that they noted this well ahead of their time. What they did is they took notice of work by two physicists named Williams and Weizsäcker, and they noted that large nuclear electric fields lead to large density of quanta in moving frames of reference. So what this means is that if you take heavy nuclei with a large Z, and you move them at relativistic speeds, that they actually produce a large density of quanta or photons. And then what they further point out is that these photons, under a very specific situation, actually behave as real photons. So again, it's very striking. They made this prediction in 1934, and they really were ahead of their time in not only predicting the process, but also having an idea of how it might be achieved, even though the technology didn't exist at the time. And so with that, let me introduce the actual experiment that we're talking about, which are ultra-peripheral heavy ion collisions. And so here on slide 11, I have an example for you of what this looks like. So in ultra-peripheral heavy ion collisions, we have a situation where we have two heavy nuclei, like gold or lead, that are traveling at ultra-relativistic speeds. And in order to satisfy this ultra-peripheral event topology, what we want to look for are events in which these nuclei actually pass one another with an impact parameter, so a separation between the two nuclei of larger than the nuclear radius. And we want that because we don't want the strong interactions that come from nuclear overlap. We only want the interaction from these electromagnetic fields. Now we know from special relativity that when these fields are traveling at speeds close to the speed of light, they'll undergo an intense level of Lorentz contraction in which the electric and magnetic fields will become contracted into the transverse plane. And so I have that illustrated for you here, where the electric field lines and the magnetic field lines become almost completely transverse. As I pointed out earlier, it was the work of Williams and Weizsäcker in their equivalent photon approximation where they first realized that it's in this phase space, so in this case where you have these ultra-relativistic EM fields, that you can actually quantize this as a flux of real photons, which is proportional, the number of photons is proportional to the Poynting vector. And we'll talk about this more as we go through the talk. So what we have here in these ultra-peripheral heavy ion collisions is a very interesting situation where we have Z, which is the charge of the individual nuclei, times alpha close to 1, which basically means that we have a large flux of photons. And we, based on predictions from our field, we have a high expectation that these types of events produce ultra-strong electromagnetic fields. For instance, the magnetic field is predicted to be on the order of 10 to the 15 Tesla, which is truly an ultra-strong field, possibly the strongest in the universe. So what I hope that I've shown you so far is that it's in these types of events that we actually have a very unique and very interesting set of conditions that may allow us to test QED in a really unique regime. And in fact, the STAR experiment tried to test some of these interesting predictions already in 2004. And there was one measurement in which the STAR experiment looked at gamma gamma to E plus E minus. However, it's a very challenging measurement. And at that time, they had only 52 candidate E plus E minus pairs. So with that, you can imagine the statistical uncertainty alone made it very difficult to make any definitive conclusions. In that paper, which is, I show you a figure from that paper on the left, they measured the transverse momentum of the E plus E minus pair and found that there was some disagreement between the equivalent photon calculation and QED calculations of the same process. And some of that was interpreted as a fact that these photons are not actually real and that there's some significant photon virtuality or virtual mass, which leads to a modification in the final state kinematics of the E+E- pair. So this is to set the scene. This has been attempted before, but the real challenge in doing this measurement is to definitively show that the Breit-Wheeler process is actually the process that's being observed and not the scattering of virtual photons, which is commonplace in high energy particle physics. Now, in order to make that point, let's look a little bit closer at the Breit-Wheeler process and what it is. So in the language of Feynman diagrams, we can express this process in terms of two lowest order Feynman diagrams. You see here one on the left and one on the right. And these two Feynman diagrams, it's important to know, will interfere with one another. And we'll talk about the effects of that as we go through. And I want to point out that the energy in the transverse plane, so specifically the transverse momentum of the two photons, gets directly translated into the transverse momentum of the E+E- pair. And that's why, like what I showed on the last slide, it's extremely important to demonstrate that we understand the transverse momentum distribution of the produced E+E- pair if we want to make the case that this is actually the Breit-Wheeler process. So keep that in mind as we go through. I want to also make a connection with this process to something else which has been measured in our field recently. So the Breit-Wheeler process, as I've pointed out, is the collision of two real photons to produce an electron-positron pair. So that's what you see on the left of this diagram. Now, there's a similar process called light-by-light scattering, in which real photons can interact with one another and scatter off one another. However, because photons don't interact directly, they must do this through a loop of some kind of charged fermion. So for instance, since E+E- is the lightest charged fermion pair, it's mostly dominant in this process. So you can have light-by-light scattering in which two real photons scatter off of each other, produce an electron-positron pair, which is virtual, and immediately annihilates back into a pair of real photons. The reason that I make this connection is because the optical theorem tells us that the Breit-Wheeler process and light-by-light scattering are like two sides of a coin. The Breit-Wheeler process, in the formalism of QED, is actually just the imaginary part of the forward light-by-light scattering. I want to bring this up because I'll show you that this is important coming forward to understand this process called vacuum birefringence. Okay, so now let's focus on how we can actually make these measurements now that we've talked about what these processes actually are. To measure these processes in heavy ion collisions, we need a way of selecting events that do not have strong interactions. So we want to select events where the nuclei don't directly interact, but only the electromagnetic fields. And the way that we can do this is by selecting events in which virtual photons excite the nuclei and cause neutron emission in the forward and backward direction. We have 0-degree calorimeters, which are calorimeters very far forward and backward along the beamline that allow us to measure this neutron emission. And what I show you here on the right is that we have very well calibrated understanding of the neutron emission for this case where the nuclei miss each other but are excited by virtual photon. And this gives us a very clean and efficient way of selecting events which don't have nuclear overlap and therefore may be candidates for the exclusive Breit-Wheeler process. And what I show you here in this figure on the left, it's kind of a pseudo Feynman diagram, is that the Breit-Wheeler process can occur in conjunction with these events where you have the virtual photons which excite nuclei that lead to neutron emission. And the important theoretical point to notice, the reason that we have these dotted lines here, is that it's been shown that the cross-section for these two different processes is independent at a given impact parameter. So we can safely look at this without biasing the measurement that we have of the Breit-Wheeler process. So from an experimental standpoint, this is crucial. And using this technique, STAR was able to collect a very high statistic sample of over 6,000 E plus E minus pairs that are candidates for the Breit-Wheeler process. So now let's look from an experimental standpoint and a theoretical standpoint. What are the signatures of the Breit-Wheeler process that we should be looking for? So one, we should expect exclusive production of an E plus E minus pair. So as I showed you in those Feynman diagrams, it's really a very clean and simple process. You have two photons in the initial state, you have an electron and a positron in the final state, and nothing else should happen for the exclusive Breit-Wheeler process. So that gives it a very clear signature. The other thing, like I mentioned, we need to demonstrate that the photons that are colliding behave as real photons. So what does this mean? For one, it means that the photons should have only the spin states that real photons allow. So specifically, this means that they should have helicity plus or minus 1 with the helicity 0 state forbidden for real photons. Now this has a couple of measurable results once the spin is transferred into the electron-positron pair. For one, it means that the invariant mass distribution should be smooth, meaning there should be no vector meson production, since vector mesons have a spin of 1, which shouldn't be possible to produce with real photons. We'll also look the angular distribution of the produced E plus E minus pair should have a preferential alignment along the beam direction. We should be able to demonstrate that the energy spectrum is consistent with the Breit-Wheeler process. And I gave you a little bit of a preview of that a few slides ago. And then finally, we should be able to demonstrate that the photons have transverse polarization states as real photons should have, and that their spatial distribution is given by the Weizsäcker-Williams distribution as expected for real photons. So this is what we're going to look for, and over the next few slides, I'll go through each of these measurements and give a little more explanation of how they help us to understand the process. So first, we can look at the measurement of the invariant mass of the produced electron-positron pair inside the star acceptance. So that's what you see in this large figure here in the data points. And as I just mentioned, we can immediately see that this is a smooth distribution falling over several orders of magnitude. And this smooth distribution is expected for the pure QED 2-to-2 scattering process. And we can even, without doing much theory calculation, can actually get an idea that it should fall like e to the -4th, where the energy is approximately the invariant mass. And what we show in addition to the data points are comparison to 3 different theory calculations. The starlight theory calculation and this GEPA, which is short for generalized EPA, are essentially simplified models to take into account the Breit-Wheeler process. And then the third is actually a full numerical QED calculation for the Breit-Wheeler process. And as you can see, though there's a little bit of variation in the total cross-section predicted for these 3 models, the data and the theory calculations agree quite well, which I have tabulated here. And as I already mentioned, there's no evidence of vector meson production even in the region of known vector mesons, for instance, of the rho, of the omega, of the phi, which, if they were allowed to be produced, should be produced, and they should be quite visible in this invariant mass spectra. Next, we can move on to the angular distribution. As I mentioned, the gamma-gamma to E plus E minus process, because of the helicity of the initial photons, it should lead to a result in which the produced electron and positron are preferentially aligned along the beam axis. And this has been expressed in quite a few different theory papers, and it's expressed in terms of this G theta distribution, where this distribution essentially tells you the distribution of polar angles for one of the daughter electron or positron. And this is a very clear signature because highly virtual photons should have essentially an isotropic distribution with respect to the polar axis. And so a measurement of this helps us to immediately determine what the helicity states for the colliding photons are. And this is exactly what we've done using these 6,000 electron-positron pairs, and the result is shown to you on the right. Now, let me go back a step. What I showed to you here is the predicted G theta distribution from 0 to pi. However, because our detector is not a 4 pi detector, we really can only measure pairs that are about 90 degrees with respect to the beam. And that puts us at this region of about pi over 2 on this plot. So the first thing that you can notice is that we actually miss a lot of the cross-section. But even in this part of the cross-section that we're measuring, there's still actually a big difference between this G theta distribution predicted for real photons and highly virtual photons. So again, if we go back to the measurement here, this drop-off is caused by the acceptance of the star detector. That's why we don't measure the full distribution that I showed on the previous slide. However, we have, for comparison, the prediction for real photon fusion into E plus E minus and the isotropic result for virtual photons. And you can see while the difference is not as drastic as you would expect in the full phase space, even in the phase space measured by star, there's actually a very significant and quantifiable difference between these two measurements. And importantly, the data is fully consistent with photons which are locked into the plus minus helicity state when they're colliding. So now let's move on to the energy spectrum of the measured electron-positron pairs. I pointed out earlier that one of the problems in the 2004 measurement, though it was very low statistics, was that there appeared to be an inconsistency between the theory prediction using the EPA for the pair transverse momentum and what was actually measured in the experiment. And I show you that here with the new high precision measurement, we can see very clearly that the data has a peak in the pair transverse momentum, which is a few tens of MeV higher than what's predicted by an EPA calculation, for instance, this starlight model. Now, I already kind of brought up the idea earlier that there have been times in the past and certain papers in the past that have brought up the concern here that maybe this change in the transverse pair momentum is actually a result of significant virtuality, which modifies the final state kinematics for the electron-positron pair. Now, over the last 20 or 30 years, there's been a lot of investigation theoretically into this process, and specifically trying to understand how the impact parameter plays a role in this process. And in order to give you an idea of how complicated this calculation can be and why it's not straightforward to understand whether or not virtuality plays a role there, I want to take just 1 or 2 minutes to go through how the calculation is done. So as I pointed out, the idea here is that you have colliding photons which produce an electron-positron pair, and that these photons originate from the highly Lorentz contracted electromagnetic fields. The EPA, the equivalent photon approximation, gives us a direct relationship between the photon density and the Poynting vector, or the energy flux of the electromagnetic fields. So this tells us the number of photons, but it doesn't necessarily tell us the kinematic distributions of the photons. And that's where doing a full EPA calculation becomes somewhat difficult, and there's been a lot of progress over the past 20 or 30 years. If we think just about the number of photons interacting, we can pretty easily express this as proportional to the Poynting vector, which we can decompose by simply saying it's proportional to the transverse electric field, which is approximately the same as the transverse magnetic field for a Lorentz boost close to the speed of light. When you take this into account, you can very easily estimate the total cross-section expected for the Breit-Wheeler process. And that's what a lot of theory calculations have done over the years. However, as I have mentioned a few times, calculating the differential cross-section, the kinematic distribution for the pair, is actually quite difficult depending on which assumptions are taken into account. These assumptions are important not only for identifying the process, but also for the discussion of the magnetic field, which will come in a few slides. So I just want to very quickly give you an idea of what this looks like. The starlight calculation, for instance, if we look at it in coordinate space, gives us a prediction for the photon-photon overlap probability, which is what is shown here, where the black disks are the two different nuclei. And the way the starlight model predicts this is that it uses a point-like source, and it disallows any production inside the nuclei. So that's why you see that there's a black disk for this nucleus and a black disk for this one. And then the prediction tells us that there should be significant photon-photon overlap between the two nuclei. And it's here where we have the potential to produce an electron-positron pair through the Breit-Wheeler process. Now, I point this out because this is a pretty strong assumption that starlight makes. And more importantly, starlight doesn't actually take into account the separation between the two nuclei when it calculates the differential distributions. Recently, there's been work on another model called the generalized EPA, which tries to build upon starlight by taking into account the production inside the nuclei. So you can see in this model, there's no longer this hard edge at the edge of the two nuclei, but instead you actually see that there can be some production, some overlap of the photons, even near the edge of the two nuclei. And this model also tries to take into account more of the differential effects on the final state kinematics. And what I want to point out is that if you actually take this into account, what we show here on the left is that you actually expect a very large effect on the pair transverse momentum. So that's essentially what's plotted on the y-axis versus the impact parameter between the two nuclei. Now, this is a crucial point because until this work was done, there have been cases in which the EPA calculations were done. And like I showed you in the 2004 STAR paper, there was disagreement there, and that was interpreted as evidence for significant photon virtuality, which clearly disqualifies this process from being considered the Breit-Wheeler process. However, if you take these fully differential effects into account, and actually what we show here are these phenomenological models called the generalized EPA, but then also you can actually do a full numerical QED calculation to take all of these effects into account and calculate a fully differential cross-section for the Breit-Wheeler process. And what I show you here on the right is that if you do that calculation, you actually get extremely good agreement between the data and the QED calculation. And this is, I'll point out here that this calculation is for photons which are real. They don't need to have any virtuality to explain the pair transverse momentum distribution. So this is an incredibly important point to make if you want to claim that we're actually observing the Breit-Wheeler process, which is by definition real photon collisions. So again, an important point. And at this point, what I hope I've shown you is that by looking at the invariant mass distribution, the polar angle distribution, and the energy spectrum, so far we have very good evidence that the photons behave as real photons and that they're fully consistent with the Breit-Wheeler process. However, over the years, there's been a prediction which is completely unique to the Breit-Wheeler process, and it's related to the fact that real photons should be transversely polarized and that the QED vacuum is actually asymmetric or anisotropic with respect to photon polarization. So let me tell you a little bit more about what this means. So in classical electromagnetism, which we've all learned since high school and college, the Maxwell equations are linear, which means that the superposition principle holds. And specifically, this leads to a unique speed of light in the vacuum. So what we have is that the speed of light is proportional to the permeability and permittivity of the vacuum. And this gives us the well-known speed of light. And there's just one of those, a unique speed of light in the vacuum. However, with the introduction of quantum electrodynamics, there's actually three important discoveries that alter this classical picture. First, we all know of the famous Einstein energy mass equivalence, E equals mc squared. This tells us that with enough energy, you can actually produce matter and antimatter. There's the uncertainty principle, which we can express in terms of the energy and the time of the process. And then there's the existence of the positron, which was predicted in the late 20s and the early 30s. And these three things together are extremely important, and they modify the classical picture, specifically because they allow vacuum fluctuations. So what this means is that if you have enough energy and you act on a short enough time, you can actually fluctuate into an electron-positron pair. And as I showed you in these Feynman diagrams earlier, because light can't interact directly, it's only through a virtual pair like this that light can actually scatter off one another. So it's with these three important discoveries in the early days of quantum electrodynamics that it became realized that this will lead to effects even in the vacuum. And so in 1936, Euler and Heisenberg presented the first calculation for a modified Lagrangian, which takes into account these effects from quantum electrodynamics. And what you can see is that it introduces nonlinear terms, and specifically this means that superposition is now broken. And it was only later in the 50s that actually Schwinger derived the Lagrangian fully within the QED framework. And at that point, you can actually express these different ideas at the one loop Feynman diagram level. Now, what are the consequences of this? Well, we still have C equal proportional to the permittivity and permeability, but now when you introduce these effects, you actually have a case where the permeability and permittivity for parallel photon polarization with the field is no longer the same as when a photon interacts with a field perpendicular. So what this means is that light behaves differently when it travels through a medium, depending on the direction that its polarization is pointing with respect to the electric and magnetic fields that it travels through. And the interesting thing is that this can be understood in terms of a medium with an index of refraction no longer equal to 1. And I like to point out this prediction here on slide 29, where the index of refraction can be broken into a real part and an imaginary part. And in this particular presentation, the point was made that the imaginary part is too small to measure because it's prefixed by this factor of 10 to the negative 91. And in fact, that is a very small prefactor, but you'll notice that it comes with a term which is like b to the 6th. And this is important because I pointed out earlier in the talk that in ultra-peripheral heavy ion collisions, we expect to have B fields that are extremely strong, on the order of 10 to the 15 Tesla. And in fact, if you plug that in, you find that this term actually comes to a level which may in fact be measurable. So, okay, I've introduced this idea of a difference between parallel and perpendicular polarization modes for light. What does this actually mean, practically speaking? And what it means is that the vacuum exhibits what's called birefringence. So there's an example in something called calcite crystal, which is a common birefringent material. And what actually happens is that light that enters with parallel versus perpendicular polarization will actually be split. So that if you look on the far side, you'll see two images where each image has been separated according to its polarization. So once again, this is a direct result from the fact that you have two different indices of refraction, depending on how the polarization of the light is aligned, in this case, with the crystal axis. Now, as I've mentioned, in the presence of an extremely strong electromagnetic field, you can have a similar thing happen, and that's what's called vacuum birefringence. So in vacuum birefringence, you don't have a medium, you have empty space, but you have empty space which is permeated by an ultra-strong magnetic field. And it's in this case where the predictions tell us that the cross-section for photons interacting with parallel polarizations is different from the interaction probability when their polarizations are perpendicular. And this leads to a similar splitting effect. And the intriguing thing is that, as I mentioned, this happens completely in the absence of any material. So it's a situation in which light traveling through the vacuum can actually be split spontaneously into parallel and perpendicular components of the polarization angle. Now this process was predicted in the early days of QED in 1936, as I mentioned. However, there's been no direct experimental evidence for this. The only indirect evidence that's been given is actually very recently in 2017, there was a measurement of light that travels through the very strong magnetic field near magnetars, and they found an enhanced degree of polarization, which is what you would expect if the light is undergoing vacuum birefringence and being split into these two different images where the polarization is completely aligned in each of the images. So that kind of sets the stage. The important thing is that in this situation, in ultra-peripheral heavy ion collisions, we have all of the right ingredients to try to measure this. So we have extremely strong electric and magnetic fields. And as I pointed out earlier, these electric and magnetic fields become Lorentz contracted into the plane perpendicular the motion. Since the photon polarization is by definition the direction of the electric field, this tells us that as these fields become Lorentz contracted, the photons which make up this field should be linearly polarized in the transverse plane. And that means that when we have collision between these two nuclei, the photons of their field will interact with different relative polarization angles. Now, what I show you on the right is the diagram for vacuum birefringence at the one loop level. And I want to make the point that this can be looked at in terms of the real part, which is where you have a photon scatter with another photon from a magnetic field, and its polarization gets modified. So that's what I show you here. But you can also look at this in terms of the cut diagram, which is the imaginary part of the index of refraction. And when you make the cut of this diagram, that's precisely the Breit-Wheeler process that we've been talking about. So what does it actually look like to measure vacuum birefringence in this situation? So this prediction has been around, like I said, since the 30s. And even for the Breit-Wheeler process, there's been predictions over the decades that the angular distribution of the produced E plus E minus pair should depend very strongly on the photon polarization angles. However, if you look back at the literature over the past many decades, it's always been assumed that this information can't be accessed in any of the realistic experiments. And even in heavy ion collisions, it was assumed until recently that because every event occurs with a different orientation, it's essentially impossible to access this detailed angular distribution information in an actual real-world experiment. However, very recently, it was realized that this vacuum birefringence effect will actually lead to a measurable cosine 4 delta phi modulation in the produced E plus E minus pair for the Breit-Wheeler process. And again, to relate this back to the real part of the index of refraction, in the full light by light scattering process, this corresponds to a cosine 2 delta phi modulation. And this can be immediately seen as vacuum birefringence because the photons are actually splitting into two different distributions depending on whether their polarization angles are aligned parallel or aligned perpendicular. Now, this modulation is predicted to be visible in this delta phi angle. And this delta phi angle is actually quite simple. It's just the delta phi between the E plus E minus pair momentum and one of the daughters. So this is actually quite straightforward to look at now that we have reconstructed this process and have access to the individual E plus E minus momentum vectors. So we can make this measurement, and that's what I show you here on slide 34. And you can immediately see a cosine 4 delta phi modulation. It's quite visible in the data. And I have for you also a comparison between the data, which is shown in the red, along with the 1 sigma, plus minus 1 sigma band, along with the QED calculation for this situation. So this QED calculation is a QED calculation of the Breit-Wheeler process. That means that it's real photons in the initial state, producing an electron-positron pair. And this particular QED calculation has actually gone to great lengths to reproduce the exact experimental scenario that we are measuring. So specifically, it takes into account the impact parameter dependence of when the nuclei collide, and it takes into account all the differential probabilities, and specifically what I've talked about in the past few slides, the different probability for interacting depending on whether the initial photon polarization is perpendicular versus parallel to one another. Now, we also show the result here in blue for the UPC measurement, in which case the measurement is actually quite significant, about 6.7 sigma. And then we also compare that to measurements at smaller impact parameters where the nuclei actually do overlap, and we have to isolate this photon-photon to E plus E minus process in a statistical way. So it's no longer the exclusive Breit-Wheeler process, but we're still able to isolate the process. And the interesting thing here is that in this case, these black data points, they're actually coming from events where the nuclei are much closer together, and therefore the fields that are interacting are actually interacting with a different overall topology. The theory calculations predict that because you're interacting in the region of stronger magnetic fields, the vacuum birefringence effect should grow stronger. And while we do see that in the measurement, the uncertainties there are a little bit too large to make a definitive claim. However, there's already evidence that as we change this nucleon-nucleon impact parameter, we're sensitive to the fact that we're overlapping the stronger parts of the magnetic field produced by these ultra-relativistic heavy ions. So this measurement actually constitutes the first Earth-based observation of vacuum birefringence. And like I said, if we take the blue data points, that's actually at the 6.7 sigma significance level. Okay, so I hope that at this point I've convinced you that there's a very wealth of information that allows us to uniquely identify the Breit-Wheeler process. What I want to do in the last few slides here is talk about how we can now take this information and apply it, like I said, as a tool for studying QCD. And in order to motivate that, I just want to remind people or introduce to people the fact that understanding and quantifying the magnetic field produced in heavy ion collisions is extremely important for many of the current and important studies being carried out in our field. And to give you an example of that, there's for instance, a predicted emergent magnetohydrodynamical phenomena of quantum chromodynamics. However, it only manifests itself in the presence of an ultra-strong magnetic field. This process that I'm referring to is called the chiral magnetic effect, in which you expect chiral imbalances, so that's imbalances between right and left-handed quarks, to produce an anomalous current in the presence of an ultra-strong magnetic field. And this has been This has been the result of a lot of work by many people over the years. However, it has not yet had any definitive observation. And my point here is that one of the required situations for this to actually take place is an ultra-strong magnetic field, which until now has not been proven to exist over a large spatial extent in heavy ion collisions. So let's look at how the Breit-Wheeler process and vacuum birefringence can give new information into this scenario. So I'm going to go just very quickly through this just to give you an idea. There's actually quite a few papers that we're working on to really bring out all of the details and all of the information that's available in this process, but this is just to give you an idea of how it's related. So as I've discussed, there's already two direct connections to the magnetic field strength. One of them is simply in the total cross-section for the Breit-Wheeler process, and the other one is in the strength or the amplitude of this vacuum birefringence process, which I mentioned a few slides ago. Now, the important thing is that the QED calculations for this process are directly related to the field topology. And so if I just take all of the measurements that I've shown you over the past many slides, and I tell you what's the field topology that was used in all of those QED calculations, that's what I show you here on slide 38 as a 2D plot of the field strength with the ion in the center. And what I'll draw your attention to here is this kind of red ring area, which is right near the radius of the nuclei, which is where the electromagnetic field should be strongest. And it's exactly in this region where we see that the field is on the order of 0.7 times 10 to the 15 Tesla. This is a field which is about 10,000 times stronger than the field around magnetars, which is the strongest magnetic field known, I should say, in the known universe up to this point. So this is an incredibly strong field. Like I said, very extreme in the sense that there's nothing else like it in the universe that we know of, and certainly not in laboratory experiments. So, okay, we can look at this in terms just of the one-dimensional radius distribution. Like I said, the field peaks near the edge of the nuclear radius. And like I said, that's important because we want to be sensitive to the topology of the field if we want to measure the field. We want to measure its spatial distribution. So what I show you here is similar to what I showed at the beginning of the talk, where we can look at the two-photon overlap distribution. And the point that I want to make to you here is that if we look at events in which the nuclei are separated by several times the nuclear radius, we have a situation in which the majority of the photon-photon overlap occurs near one of the nuclei. And as I just showed you on the previous slide, that means it occurs in the region where one of the electromagnetic fields is at its peak strength. So let me say that again. What this plot is showing you is the probability for photons to overlap. So the fact that the probability is high here means that you have one photon from this nucleus interact with one photon from this nucleus, and the location at which they interact is in the region where the field is extremely strong from this nucleus. And so if we actually just take the EPA calculation, we can see that this gives us a prediction for a very simple scaling of the total cross-section. So for events which are very far apart in their impact parameter, we should expect a scaling of the cross-section which goes about like the peak magnetic field strength squared times some constant, which takes into account all of the numerical constants. And so I just want to show you that here on slide 41, that we can actually look at these QED calculations at large impact parameters and immediately see in this plot that you show in the lower right that the expected scaling of the magnetic field follows something very close to this b squared times some constant. And I just want to point out how simple this relationship is. Now we're at the very beginning of these types of measurements, but what this tells us is that if we make multiple measurements of this process over the coming years at different energies, at different impact parameters, possibly in different colliding systems, this gives us a tool to map out the magnetic field in those different scenarios. We can look at another impact parameter, which is much closer, where the nuclei are actually overlapping. And again, using a very simple reasoning, we can expect that the magnetic field will no longer scale like the peak B field squared, but something closer to the peak B field to the fourth. Now, these results are still kind of a work in progress. They're going in a paper that we're hoping to have out quite soon. But the point that you can see already is that you don't quite get to B to the fourth, but you get to something like B to the third power. And the point that I want to make by comparing this to the previous example is that as you scan through different impact parameters, you actually have a different scaling relationship with the field, which is exactly what you want if you're going to be sensitive to the topology of the interacting fields. So as I mentioned, if we, over the coming years, if we're able to make measurements at different impact parameters and look at how the cross-section changes, this gives us a handle on constraining the initial magnetic field in these collisions. Now, I want to point out too that the vacuum birefringence process is extremely sensitive to the topology of the fields, and that there's actually already quite a few papers from the authors of the QED calculations in which they explore that. So there's quite a few different ways for us to approach this, and it's very exciting to me to see what the future will hold now that we have this new tool. Now, in my last minute or two, I just want to give you a little bit of an idea of how this process may be used in another way, which is that in heavy ion collisions, we don't just have a magnetic field which is produced and then immediately dies, but we expect that field to actually live for some short or possibly long period of time. And that's actually a huge open question in our field, which is how long does the magnetic field live? And specifically, can it be trapped by the medium that's produced in these heavy ion collisions? If that medium is conducting, then there's the possibility that it can actually trap the initial magnetic field and through Faraday conductance allow it to actually live for a longer period of time. Now, I've pointed out that there's very significant consequences from super strong electromagnetic fields. So the question then is, are there any consequences of an electromagnetic field that's trapped in the medium for a long period of time? And there's already been a few proposals about how the Breit-Wheeler process could be used to test some of the different scenarios. So I'll just point out that there's been two main predictions in our field, which is that if you have, what I show over here on the right is the lifetime of the field. So if you have nothing interesting besides the vacuum going on, you produce a very strong field and it dies very quickly. But if, like I said, if you trap that field, you have the possibility that the electron and positron pair that are produced will feel a strong magnetic field and therefore undergo Lorentz force bending as they travel through that field. And if in fact there is Lorentz force bending, that should affect the final state kinematics of the measured E plus E minus pair. Now, this is one possibility. The other predicted possibility is that the electron or positron could actually travel through the medium that's produced in these heavy ion collisions, in which case you'd have something like Coulomb multiple scattering through a quark-gluon plasma. This also would affect the final state kinematic distributions, and therefore it would lead to some perturbation on the vacuum-only result. And if that difference between the vacuum-only result and the result with these final state effects is large enough, you may be able to use it as a tool to actually measure these effects. So I just want to point out that STAR has actually taken the first step to do a measurement like this. So I already pointed out a few slides ago that we're able to measure the gamma-gamma to E plus E minus process, even in the case where the nuclei overlap with one another. It's a statistical process, but nevertheless, we're able to remove all the backgrounds and all the production from all the other processes and really look at this process from the gamma-gamma to E+E- process. And you can immediately see that at these smaller impact parameters, called 60 to 80%, we have a significantly larger transverse momentum of the pairs. And like I said, this could be considered evidence for these medium effects. However, I'll just get to the punchline. However, I've already made the point throughout this talk that these QED calculations actually predict a very large effect from the field topology alone, which means that as you change the impact parameter, you're colliding photons from drastically different parts of the fields that come from significantly stronger or weaker electromagnetic fields. And this leads to a direct impact on the measured electron-positron pair transverse momentum. So when you take this into account, you actually see that the QED calculations with no additional effects already describe the situation extremely well. I will point out that with the large uncertainty on these red data points from the smaller impact parameters, there's still room in the data for something like 14 MeV of additional broadening or of an additional effect. So we haven't completely ruled out these two different phenomena that I talked about on the last slide. But if they do exist, they may be smaller than was originally expected. So we're looking forward to comparing to the data that's coming out. And like I said, I think there's a lot of exciting opportunities to learn about what's happening in these extreme situations. So with that, I'll go ahead and end and take some questions. And just to summarize, these measurements provide the first definitive measurement of the exclusive gamma-gamma to E+E- process so that we're able to definitively say, yes, we're observing the Breit-Wheeler process. And like I showed you, the angular distributions are actually a direct result of the photon transverse polarization, which gives us the first Earth-based observation of vacuum birefringence. Together, these give us the information we need to begin characterizing the super strong electromagnetic fields that are produced. And as I mentioned, this is evidence that heavy ion collisions actually produce the strongest magnetic fields in the universe. And not only that, but that they produce these fields over an extensive spatial distribution. So a lot more work is needed to extract all the information. But like I said, I think there's a lot of exciting opportunities ahead using this new tool that we have. Thank you.
Thank you very much. Anyone who wants to ask a question, please raise your hand or chat. And I see Orlando. So let me start with him. Are you unmuted? I guess not. Okay.
Hi.
Hello.
I want to ask one question. It's possible to test this scenario in, for example, you tested this in gold-gold collision. You saw the plot, no? This cosine 4 phi behavior.
Mm-hmm.
Can you have some similar plot for proton-proton collision in the or different collision nuclei to see if you still have this behavior? Because if this effect is correct, you don't expect to see this cosine 4 phi in the data. Should you have this plot for this?
So STAR is working on measurements in uranium-uranium collisions and also copper on gold. Because the electromagnetic fields from each of these different types of nuclei will be different, you do expect a different result in each case. Mm-hmm. I think I heard you ask about proton-proton collisions.
Yeah, because in this case you don't have any effect, which I understand. No?
So there's a couple reasons why proton-proton collisions are a little different. One is that because the fields go like z squared, so z being the charge, the cross-section is hugely suppressed in proton-proton collisions. But the other thing that I pointed out is that the cosine 4 phi modulation is really a result of the spatial extent of the field, because it depends on the varying angles that the two photons interact with. And when you have proton-proton collisions, you have much more of a focusing on these points, and you don't have this nuclear dissociation process, which allows you to kind of tune the impact parameter. And this makes it extremely difficult to actually access this spatial distribution information. It still may be possible, and I think if anything, this work shows that people should think out of the box and look in places that it's been assumed in the past you couldn't necessarily see this, but I think it will be more challenging than in heavy ion collisions.
Okay. Can you ask another question, Giorgio?
Sure. Anyone? Sure, go ahead. Anna.
Okay.
Anna is next in line. Yeah.
My another question is, Sten, you are working in the heavy ion collision where you have the Z times alpha is a big number. Mm-hmm. You not expect some very strong effect by the radiative corrections?
By the what corrections?
Radiative corrections.
Yeah, okay, yeah, so higher order corrections.
Yeah.
Yeah, this is actually, this is a very good question. So there's no direct evidence for Coulomb corrections. There are some higher order effects which are taken into account in one of the QED calculations due to final state soft radiation. But the interesting thing is that the Breit-Wheeler process is actually by definition this lowest order process where you have two photons interacting. However, there are predictions that in such strong fields, the cross-section for the higher order processes, where you have multiple photons simultaneously interact, is actually not small compared to the first order process. And so this is a very interesting direction for us to look. As far as I know, no one has ever looked for events in which you have photon-photon to, for instance, 4, so 2 electron-positron pairs. So this is a very good question, and it's an important thing for the field to investigate going forward.
Okay. Anna, thank you.
Hi, hello. Can you hear me?
Mm-hmm.
Thank you very much for the talk. It's very exciting to see finally some experimental sign of the magnetic field. We've been waiting for that for such a long time. Mm-hmm. So my question is that in the QED predictions, in the QED calculations you mentioned, mm-hmm. I understand it was not taken into account the time variation of the B field, of the magnetic field. Is that correct?
It depends on what
you just consider you just consider there is a constant magnetic field, and then
that's right. So these calculations use what's called the external field approximation. So there's essentially mm-hmm. no time variation in the field. Mm-hmm. And I think for the vacuum case, that's maybe not a bad assumption, but certainly for the case as you actually have nuclear overlap, the whole thing becomes more complicated, and actually there's a good reason to believe that there are maybe more complicated things going on. And for instance, it's not even clear once you have nuclear overlap that you can treat the field coherently from the whole nucleus. Maybe it's only the field for the protons that don't interact, that continue traveling. So there's quite a few open questions that I think this is a really good question, and I hope that it will be continued to be studied. But you are right that the current calculations use this external field approach.
Okay, but I mean, even for the vacuum, because the magnetic field drops very sharply. It's mm-hmm. really, really quick. So I would expect even for the vacuum, it would, have some influence. And the fact that your data fits very well the QED prediction, at least a little bit, I would expect it to affect it. Why?
Well, so maybe let me clarify. The overlap time is taken into account in the QED calculations. It's just that you assume that the field itself is not being modified in any way as they're overlapping. But this plot that I showed you earlier is really the field from the overlap of these two ions. And that does take into account the fact that they're traveling past each other and the fields are moving through each other. And these QED calculations do essentially take this part to first order into account.
Okay, so you just consider your interval of time, you consider your process can happen very small, so you don't have to worry about that. Is that?
And there's actually, like I said, this is a very good question. And to be fair, vacuum birefringence is normally thought of in terms of a photon interacting with a static field. And the point that you bring up is that that's not necessarily a good assumption in this scenario. Now, there has already been a lot of work done to express vacuum birefringence at the one loop level, which is more independent of those assumptions on how static the field is. But like I said, I think it's a very important set of questions, and I look forward to some theory work which continues to look into what we can learn about the field, especially its lifetime, through these measurements.
Okay, thank you.
Okay, any last questions?
Yes. Yes.
Who's speaking?
Lance.
Oh, yeah. Hi, Lance.
Yeah.
Please go ahead.
So, no, I have to reiterate Anna's question, because the PT of the electron-positron pairs you were looking at is like 0.2 GeV. And the frequencies you expect in this magnetic field are on the order of a GeV. So I'm a little surprised that a constant magnetic field approximation is giving you reasonably good agreement in this case. I mean, maybe you just need to explain to me a little bit better what you mean by the full QED result, because I was also confused there by the fact that sometimes it sounded like you said the full QED result involved photons that are on shell, but at the same time using something about the magnetic field of the ion, the magnetic fields produced by the overlapping ions. So those are two incompatible statements for me.
Mm-hmm.
Yes, and so there's I think there's reasons for this, and why people have not actually looked for this so directly in the past. These are all related measurements. So the pair momentum is in this calculation is directly resulting from the energy spectrum that you expect for the electromagnetic field distribution. Okay.
Brilliant.
So you can do this calculation assuming that the photons are virtual. You can do that, in which case the spin states are not necessarily locked into this helicity ±1, and specifically you don't have this position momentum correlation between the polarization vector and the transverse momentum vector. It's when you make the assumption that these are actually on-shell photons that you explicitly get this prediction for the polarization directions. Mm-hmm. And it's in this case that you then expect the vacuum birefringence effect, or this cosine 4-phi modulation, which is a direct result of the fact that the polarizations are now over the different spatial distributions colliding with different relative angles. So I understand that there's, I understand some of the difficulty in understanding how these different things come together, but the point is that the measurement actually is quite sensitive to how you treat these photons. And it's specifically this cosine 4 delta phi modulation, which is directly a measurement of the spin states of the photons. And this prediction is you only get this prediction for this strong cosine 4 delta phi modulation when you assume that the photons are on shell with transverse linear polarization.
Yeah, that's fine. I mean, I expect that to be a good approximation. That approximation mm-hmm. that approximation I think is very good, right? It's in some ways the motivation. You could say that's the motivation for Weizsäcker and Williams.
Mm-hmm. Exactly.
What is less clear to me is treating the magnetic fields as constant.
So maybe when I said constant earlier, it's a bad use of words. It's the external field approximation, which means that the field in the rest frame of the moving ion is constant, but the overlapping field is not constant. And I think that's maybe the distinction I didn't make earlier, is that in the rest frame of one of the ions, or traveling along with one of the ions, there's nothing changing. It's static, which means that in the boosted frame, you can treat them as these external fields, but that naturally leads to this type of lifetime, which I showed from this vacuum curve. So
if you're in the rest frame of one ion, there's no magnetic field. There's the magnetic, there's the, the high frequency magnetic field of the other ion.
That's right. Yeah. Sorry, in the center of mass frame, the point is that the fields of the two nuclei are external to the nuclei, right? And so when they overlap, you'll naturally get this type of lifetime of the overlapping field. And this is taken into account in the QED calculations. I think what I said earlier when I used the term constant was probably a bit confusing. Yeah.
Sure.
The important thing, though, if you look back at some of the literature, is that the lifetime of the field does need to be constant with respect to essentially the Compton wavelength of the electron in order to produce it in such a way that it's at this lowest order. And like I said, I think there is definitely more work that can be done to look for these higher order effects and to look for some of the other interesting predictions of strong field QED. But those are things that can be done in the future, I think, in addition to what's already been done.
Yeah, so certainly the ability to discriminate the ultra-peripheral collisions is quite cool. That does look like a very promising, capability that you've developed now. So yeah, doing future measurements on this is certainly something we'll be watching.
Mm-hmm.
Okay. Any last minute questions? If so, I'm stopping the recording. Thank you very, very, very much.